This is posted on our website. There's some tutoring hours. Your instructor, in my mind, should be your line of defense. But, you know, you can't always make it come in and see me. People are busy. But I think it'd be much more efficient. You can get through and get you from point A to B a lot quicker. But there's tutors that are also available. This is online on our website. On. What's the concentration of water? Or is there such a thing? Can you say the concentration of water is, have a beaker of water? Do the question really give the answer, why not? Because what is concentration? Think of the molarity. Little stuff or liters of solution. We'll take that beaker of water. You have so many moles of it, you can just mass it and convert it into moles. Measure the volume, divide the two, you got it. Water, you're going to come up with 55.4 moles of water per liter of solution every single time. This little guy showing his thumb there, or his finger, Alexa, he went swimming, comes out, fingers are all looking like this. Is the water, he's swimming, imagine him swimming. Is the water more concentrated inside him? Outside. Do you agree? Because it's water. You can't get it any more concentrated. Okay? Now what does nature do? Nature, you have this region of where things are more concentrated. Do things naturally spread out and get more concentrated? Things disperse. Right? So when that little guy's swimming, Mariella, did the water go inside him or did it go outside of him? Right? Where was the water the most concentrated? Was it inside or outside of him? What did we say? We said it was outside. So the water must have gone inside that kid. That kid walked out of the swimming pool heavier than when he walked in. He's got to run to the bathroom, I bet, in 2 minutes, too. He probably did take care of it. Right? So, because look at those fingers. Swelled fingers. Those aren't shrunk fingers. Those are swelled. He sucked up water. Right? Lettuce. Same thing. It's all wilted. Why? Because it's water. It needs some water. Right? So how can you get water inside the lettuce? Let's see. Where is it? Here it is. So it looks, Nick, that you have this wilted lettuce, and you put it in some cold water in the fridge, leave it there. Does the water go inside the lettuce, or does the water go from the lettuce to the little pan of water? It goes inside. Because where's the water most concentrated? Outside the lettuce. have things go the opposite. Right? Take a snail. Snail's wet on the outside. You dump salt on it. So you have this really, really concentrated salt water. Right? In fact, it's so concentrated, the water inside the snail is more concentrated. All the water is going to end up what? Coming out. That would be one of the worst ways to die, right? And the movie is one of the most disgusting things I've ever seen. It would be great for a horror movie, but no one would understand it except for you 20 people sitting in this room, right? So it's never going to make it to a horror movie. Osmotic pressure is what we're really getting into. Let's take a look at this animation. Osmotic pressure.
Solid molecules migrate through the membrane from the solution of low concentration to the solution of high concentration. A concentrated glucose solution is added to an inverted funnel with a semi-permeable membrane, and the funnel is placed in a beaker of pure water. Water flows from the beaker into the funnel. The upward flow of solvent stops when the pressure of the solution above the membrane equals the osmotic pressure, pi.
Okay.
The membrane.
Let's back up here. What is... I think they did a pretty good job in that animation, actually, to tell you what it is. More specifically, only what? Water. Everything else is too what? Too big. Look at the holes, right? So water's the only thing that can fit through those holes. Destiny, is it only one direction? Or can water go both ways? Go both ways. Why not, right? Oh, it is going both ways, except it's going, Ray, more in one direction than the other. Which one is it? Towards the glucose side, right? Because water's more concentrated on the other side. Okay? So, yeah, it's going faster that way. So there's going to get to be more and more water on that side, and that the level in this thing is going to keep going up, right? Because the water's going in there. Because the glucose is supposed to be in here, right? The sugar solution. So water goes through the membrane and in here. That's going the other direction too, but not as much. The rate isn't as high. So the level keeps going up. Forever? Lewis? No, Lewis. It's going to stop sooner or later. Why? There's going to be an equilibrium. Now, things don't stop, right? Water's still going through those holes. But the level stops because the rate... the rate is the same. Now, the only way you can make the rate the same... Now, why would the rate be the same? Why would the rate increase the higher that column got? How is this pressure idea generated? How is pressure generated? This column is higher and higher and higher. It's hitting faster, hitting harder. Pressure, right? Look at the height. It's gravity, right? And you have this column of liquid that's getting higher and higher and higher. So you're increasing the pressure on that, right? But you're right, Nick. At the molecular level, that's exactly what's happening. They're hitting more often and they're hitting harder. But that's pressure. So it's going to stop. Well, the level's going to stop. And then the rates are just the same going in and out, going both directions. Now, let's say it hasn't quite, let's say it just started, right? So that this little level guy is way down here. I could prevent the level from going up by doing what? Well, not adding or subtracting anything, though. Adding up or blowing on the end, adding some pressure, blowing on the end. But now I have to blow with just the right amount of pressure. If I blow too hard, the level is actually going to go, the rate going out is going to be faster. So I got to blow at just the right pressure so that the guy stays the same. The technical word for that is what pressure? Osmotic pressure. That's the exact pressure that I have to apply, whether it be with a little piston or blowing on it or whatever. You could, well, yeah, then you're going to, there's nowhere for the air to escape. You tip the top, but that, it would still move up a little bit. So you actually have to apply some pressure on here. The exact amount of pressure, you can calculate it. Here it is using this equation. Okay. Osmotic pressure is supposed to be, although that Greek symbol, you recognize it? Pi. All right. Pablo, what were some units for pressure? Because pi is supposed to be pressure. Units for pressure. What were some units for pressure? What did we use? We'll use millimeters, ATM, Pascal. So let's see if we can figure out what the units are going to be for pi. Mallory, you recognize R? What was it called? You don't remember what it's called? You remember what the number was? Yeah. Not 0.082. We're talking about that big R. Liter atmosphere. It's on all the handouts and things I give for the test, right? 0.08. It's called the gas constant. It was in the ideal gas law. Okay. So looking at that, Vanessa, I bet what? The units of pi are going to be what? Every single time. It's going to be ATM. Okay. So that means we got to get the liters, the moles, and the kelvins to cancel in that equation. Victoria, the big T is probably the big K, the Kelvin. Right? How did we convert things into Kelvin again, Eddie? You remember? If you have so many Celsius, you add 273. Okay, so that'll get rid of the Kelvin. So this guy, the T must be the Kelvin. The big M then must be what unit, Jessica Rojas? Oh, well, you're on the right track. Liters per mole have to cancel. So it has to be moles over liters. Otherwise, they won't cancel. So this guy has to be moles over liters. Otherwise, it won't cancel with the units in the big R. Javier, do you recognize what moles over liters is? What's the name of it? Give you a hint. Moles of solute over liters of solution. It was called molarity. Big M, molarity. When I first look at this osmotic pressure equation, I thought big M was molar mass. But it's not. It's molarity. It's the concentration. Molarity. Okay. This looks a lot like last class period. Except we've got a whole other column of equations. But they all have this bloody I in them. Adrian, it says we're supposed to use the equation with the I instead of the one without when you have an ionic solute, right? That's what's up here. What's an ionic solute? How do you know you have an ionic solute rather than a molecular solute? Ooh, he answered it for you using the nice guy. A metal. You see a metal, and it has to be a what type of compound? Ionic. Okay, that's the first phase to figure. To see a metal, then you know it's an ionic compound. Then you have to use the equation with the I's in it. They want to know the new boiling point or osmotic pressure or whatever. If you have an ionic compound, you have to use the equation with the I in it. I'll give you some hints here. See if you can follow it. If I have KCl, my little I is going to be 2. If I have aluminum chloride, my little I is going to be 4. If I have iron sulfate, my little I is going to be 2. Okay. You want to see what's going on here? Oh, you're getting close. It's the number of, technically not atoms, ions. Ions. When you break these ionic compounds up, how many ions do you get for every formula unit? Like KCl, that breaks up into K plus. You really don't care about the charges in this. You just want to count stuff up. So there's going to be 2 ions. Aluminum chloride, remember how this works? It breaks up into Al. And how do you know the charge on it? Move it up from the chloride guy. And then you have how many chlorides? 3 of them, because that subscript's a 3. And you know the charge is a minus because of the little 1 down there. Add the total number of ions. So I have 3 chlorides and 1 aluminum, totals 4. Why is the total for iron sulfate 2? Yeah, right? If you remembered, sulfate is one thing, SO4 minus 2, then you'll recognize, I have this iron and I have this sulfate. Whether you know what the charges are or not, right? They're both plus, well, one is plus 2, the other one's minus 2. But the point is sulfate doesn't break up. It's 1 ion. That's why you just have 2. So that's the game you're going to play to figure out what the little I is. Okay?
So we're just going to put the I, like in the first one, you put 2?
Yeah. If it was KCl, little I is going to be 2 in every one of these. Remember which one you're going to use. Okay? If you don't see a metal, use this side. Right? You don't see a metal. Molecular solutes. Okay. There's one last little concept. I don't think there's any homework with this, but I have a demonstration of it. Most solutions, most every single solution known to man, like salt, you shine a laser through it, you can't really see anything. Okay, there's a little bit. You can't really see the light being scattered. The light just shines right through it. But if you have some big molecules in there, I'm being recorded. If you have some big molecules in there, right, they scatter the laser light. You see it going across? So even though the solution looks clear, there's actually really big molecules in there, so big enough that they can scatter laser light. And you call those colloidal solutions. So fine. I don't think there's any homework on that. Okay. I think this is the toughest question you're going to come across, so let's Jessica Vaughn just go ahead and start. An aqueous solution contains 0.296 grams of a polymeric unknown compound. If there's 125 mils of solution, temperature is 25, osmotic pressure 2.58 millimeters of mercury. What is the molecular weight of the unknown? Now, hopefully, you have no idea how to solve this, because then you'll understand everything I'm going to say here. Okay. Jessica, you have no idea how to solve this, correct? Just say yes. Okay, she has no idea how to solve this. So, what are they asking? Molecular weight. Follow logic. We're going to be using it. Follow logic. Molecular weight. First thing, look at all these bloody equations, molecular weight in one of them. Remember, because that's the game. Is molecular weight in there? Do you see a variable that stands for molecular weight? No. It's not there. So, follow logic. Start with what they want. Molecular weight. Molecular weight is what? Yeah, moles are in there. Grams over mole. That's what molecular weight is. Grams over mole. Mariella, questions kind of changed now. We're halfway there. I don't know if you see it. Yeah, because she said use the grams of the stuff. The grams, so the molecular weight of the unknown is the equal sign, grams of unknown over moles of unknown. She recognized the grams of unknown is 0.296. We're halfway there. Where's after moles? Bless you. Find it and we'll have it. Okay. Matteo, do we have an equation that has just moles? Then we can solve for it. Just moles. No, right? So what was Eddie's advice? Plug in what you have. I think that's genius. Nick, what do we have? We plug into what? Yeah? Yeah, so where are we going to start? The osmotic pressure equation, right? Plug in what you have. Figure out what you got and plug into that equation, because it's going to be that way every time. There's going to be one thing in that equation you don't know, and that's what you're going to solve for. You said the osmotic pressure equation. So are we going to use the one, Destiny, with the I or without the I? Because we have two choices now. Without. She is right. Why? Exactly. That's what I saw too. Molecular. Right? I was going to go off on a big spiel what a polymer was, but I don't need to because it says molecular up there. So don't use the I. M-R-T. Okay, Ray, stick to Eddie's advice. Plug in what you know. Let's start. Let's fix it. Let's fix it. Like he said, let's add 273 to it. 298 Kelvin. Okay. Lewis, what else do we know here? Oh, yeah. You look it up, right, on the top of the quiz or whatever. Yeah, the 0.0821. Liter atmosphere per mole Kelvin. Aldo. We're going to keep doing this, plugging in stuff we know until there's one thing left. Right now we know the T. We can plug in something for the R. But there's two things left. So that means there's one thing we got to plug in yet. Pi is the osmotic pressure. And they say it's 2.58. Yeah, we have to convert it to what unit? ATM, because that's what the R is in. And you look at the top of the quiz, or you just remember, it's 760. .58 about 0.00339. Or you could just say 3.39 times 10 to the negative 3, right? Okay, so now we know all that stuff. We can plug it in. We have, and we quit because now there's always one thing left. Right? We're going to be solving for big M. And I'm just leaving the units out because we fixed all that. So Pablo, how mathematically are you going to solve for big M here?
Divide 0.021.
Yeah, you hear what you said? Divide this 0.0339, divide it by the 0.0821, divide it by the 298, and you'll have it. Okay, about 1.39 times 10 to the negative 4. Okay. Mallory, we plugged in what we knew, and we got this big M. What we're after are these moles. We're still after the moles. Then we can plug it in and get molar mass. Do you see what to do? What was big M? Yeah. Yeah, she's looking for her sheet, right? That's okay, but you see what she's doing? She's looking for her sheet. Exactly what you should do. Yeah, moles of solute, and we could write, what? Unknown molecular, moles of unknown, yeah, moles of unknown, that's a good one. All over liters of solution. Okay. So, we know what big M is. If we know what liters of solution is, man, we can find moles of unknown. What's the liters of solution? Vanessa Vasquez, did they give it to us? There it is. But it's in the wrong unit? Convert it. Divide it by 1,000, right? If you're not sure to move, yeah, 125. If you're not sure if you can't do it in your head, you have to actually work it out. Really just moving the decimal place over 3 places. So my big M is going to be 1.39 times 10 to the negative 4 has to equal my moles all over 0.125. So I have to bring it up to the top, so multiply it times 0.125. Multiply 1.39 times 10 to the negative 4 times 1.125. 1.73 times 10 to the negative 5. All right. Now I can finally get my molecular weight. .296 grams. Right? Because now once we get our moles, we're just going to plug it in up here. Plug it in right here. 0.296 grams over 1.73 times 10 to the negative 5. Now I got a huge, huge answer. 17,066. Something like 17,000 and something. Okay. Have you ever found a molar mass by adding stuff up on the periodic table and got 17,000? But no, right? So it looks like a mistake. But that's why knowing what a polymer is really, really helps. It's just this compound that's repeated again and again and again and again, and it's all covalently bound together. So, okay? Okay? So that's why it's going to be huge. Okay? Well, molecular weight is grams over mole. You should get around 17,000 grams per mole. Okay. Okay, let's take a look at this one. Now, let's back up a little bit. Do you see what we did? You follow logic, right? Because some questions are going to be easy. We look what they're after. You look for an equation that has it. If it doesn't have it, well, then just write down what they're after. In this case, it was molar mass, so grams over moles. Now you're looking for grams, and you're looking for moles, right? Again, what you know, Eddie's advice, it'll work out. Genevieve. Yeah? What's that? Oh, we'll fix, it's a calculator problem. Let's fix it after class. Okay? I bet you're plugging it in wrong. Okay, so don't ask after class. We'll figure it out. One more question here, and then we'll call it a day. Victoria, we've got a mountainous location. The boiling point of pure water is 95 degrees Celsius, right? Lower pressure, so you're up high, things are going to boil at a lower temperature. How many grams of sodium chloride must be added to a kilogram of water to bring the boiling point back to 100 degrees Celsius? Victoria, where are we going to start on this? What do you mean? Oh, she's talking about. Okay. Yeah. Okay. She's thinking about what formula to use, and she's talking about the CM one. I think you're talking about this stuff, right? I think that's a good idea because they're talking about boiling point. But you have to know, Eddie, which one. With. Because they're just see a sodium. Plug in what you know. So what do we know, Jessica Rojas? What are you going to plug in? Okay, the 100 degrees Celsius. Now that delta TB, that is the change in boiling point, not the new boiling point. Delta TB is going to be what? It's going to be 5 because the change. Delta TB is the change in boiling point. And it was 95. They want to make it 100, so the change. Because that's what that triangle means, the change, right? So delta TB is going to be 5. Javier, what else do we know? Oh, he's talking about KB? You pretty much have to have a table or something for it, right? I don't know if he doesn't have a table. Let's help him out here. The KB for water in that equation 1 handout, or exam 1 handout, is 0.51. I see. So this is 0.512. Now remember, you keep plugging stuff in until there's only one variable left. So we either got to know I or CM. I is going to be 2. CM. So you may not have known how to solve this, but let logic tell you. So solve for CM. Something will stare at you. So 5 divided by 2 divided by 0.512. Yeah, well, that's what I got too. Well, 4.88. Okay. Adrian, we're after grams of sodium chloride must be added to 1 kilogram of water. Molality. Use the molality equation. Yeah. Okay. Now let's help us out. Instead of writing solute, let's write sodium chloride. And instead of writing kilograms of solvent, let's write kilograms of water. There's our equation. Now, grams of sodium chloride isn't in there. We're going to solve for what? Moles of sodium chloride and use, what's the technical word? Molar mass to get it into grams. And we'll have it. Okay? So try it. Plug in what CM is. Oh, yeah, you're right, because this is, but just show all your work so when you look at it, right? You know what CM is? Plug in the number of kilograms of water, solve for moles of sodium chloride, convert it into grams. Right? It'll work. Okay. Okay. Let's see. Anybody get the molar mass sodium chloride? 58.5. Thank you.
And 285.
You had 285?
And you put in the point.
Okay, several folks got 285. So hopefully you're getting 285. Okay. Hopefully you're getting 285. Okay.
I forgot that F started with the freezing. That was.